Good day to you from ChemHelp ASAP. This video provides practice for completing reaction schemes for different transformations that involve enolates. Check the video description to find links to printable copies of these problems and their solutions. There will be links during the video that will connect you to other relevant tutorial videos that you might find helpful. What kind of reactions involve enolates? Well, there are many, but I'm going to focus on three reactions in this video. First, we have the enolate alkylations. Enolate alkylations generally start with a ketone. The enolate is specifically formed by deprotonation of an alpha proton with LDA in the first step. In the second step, after the enolate has been formed, you add the alkyl halide to form the alkylated ketone as the product. This is normally a two-step process: deprotonate and then alkylate. So, 2 steps. The second type of reaction is the aldol reaction. The aldol reaction starts much the same, and the first step is a strong base like LDA forming an enolate from a ketone. In the second step, another carbonyl compound, often an aldehyde, is added. The enolate attacks the other carbonyl to make a tetrahedral intermediate. The third and final step is addition of water or some other proton source to protonate the tetrahedral intermediate to form a beta hydroxy ketone. So the aldol reaction is often, not always, characterized by these three steps and a beta hydroxy ketone product. The third type of reaction is the aldol condensation. The aldol condensation normally has just one step. In this one step, you throw together all your reagents, the ketone, an aldehyde, and a weaker base like hydroxide or an alkoxide. Throw them together and let the reaction do its thing. So while the condensation has just one step from an experimental design standpoint, mechanistically there are many steps. The base is forming the enolate. The enolate is attacking the aldehyde. The tetrahedral intermediate is being protonated by the solvent, and a couple more steps lead to elimination of the beta hydroxy group. The overall product is an alpha beta unsaturated ketone. Note that I'm only discussing ketone enolates in this video. The rules that apply to ketone enolates generally apply to other enolates, like those from esters or nitriles. Now, these general trends do not hold for every single alkylation, aldol reaction, or condensation. We will encounter some exceptions in the problems in this video. Okay, that's enough talk and background. Let's do the problems. Problem number 1. So we are given the final product as well as the starting material, and we need to figure out what our reagents are. Well, if we look, we start with a ketone, no surprise there, and what we finish with is the same ketone with this extra alkyl group. So this is going to be a ketone alkylation and an enolate alkylation. So we need to form an enolate, so that means we need a strong base to deprotonate our ketone. We want to deprotonate at that alpha position. There's that alpha carbon, and note that our alkyl chain is 3 carbons, so that puts some parameters on what needs to go in the box. So our first step is going to be forming the enolate. Typically for clean enolate formation, clean, complete enolate formation, you need an extremely strong base like LDA. And then in our second step, we add an alkyl halide, and our alkyl halide needs to have 3 carbons. So my favorite halide is bromine, and there we go, 1, 2, 3, and there is our product. So problem 1 is a fairly straightforward enolate alkylation, a ketone alkylation. Okay, for this next problem, we start with a ketone, again, not a shocker there, and we finish with this product. So let's classify this product. If we can identify what type of product it is, that can help us determine what type of reagents we need. As we can see, we have a ketone and then alpha beta. This is a beta hydroxy ketone. So this is going to be an aldol reaction. Aldol reactions form beta hydroxy ketones, and they form them by having an enolate attack an aldehyde. Now, the beta carbon comes from our aldehyde. This alcohol oxygen comes from the aldehyde. So this is where our ketone was. So let's keep that in mind. So first step, we have to form our enolate. Our enolate comes from that alpha carbon, and we're going to deprotonate that with LDA. And our second step is, once we have the enolate, we're now going to add our aldehyde. And it's going to be a little smushed in this box. But our aldehyde contains that carbonyl, and that carbonyl right there, that carbon is going to become our beta carbon. And so that means we need, off of that carbon, we need this cyclopentane ring. So, or cyclopentyl ring. There we go. There's our aldehyde. So the enolate from the first step attacks that carbonyl. That gives us a tetrahedral intermediate. And we need a third step. Typically for aldol reactions, we'll see 3 steps. We need some kind of proton source. I'll typically say water, but it could be anything. It could be an alcohol, methanol, but some kind of proton source, some weak acid to generate, to get our OH on that oxygen. So that's problem 2. Problem 2 is an aldol reaction. It does have our expected 3 steps, and we have an aldehyde being attacked by the enolate. All right, for problem number 3, all we're given is the structure of the product. So what kind of product is this? Well, this is a ketone that is alpha beta unsaturated, and therefore we know this is a product from an aldol condensation. And if this is going to follow our pattern that we saw in the introductory slide, then we would expect to have a ketone as our starting material and a mixer reagents that's going to give rise in one step to this aldol condensation product. Now let's identify our ketone. Our ketone includes the alpha carbon and nothing else. So our ketone is going to be cyclopentanone, and there's our alpha carbon. And the source for these carbons, this is going to be an aldehyde that gets attacked by the enolate. So again, the beta carbon are going to be from our aldehyde carbon. So we need that. Tell you what, and just to make this clear, what else is off that beta carbon? There's a hydrogen. So off of this, the carbonyl that becomes our beta carbon, we're going to have that hydrogen and the R group, which happens to be a phenyl. So these 2 groups on the beta carbon are the 2 groups that are on the carbonyl. Now, for the aldol condensation, typically you use some base like sodium ethoxide. I'm going to call sodium ethoxide a weak base. It's not really weak, but it's not a super strong base by organic chemistry definitions. So this is a nice modest base. Will form our enolate in low concentration. It will attack the carbonyl, form a tetrahedral intermediate, and then through a series of protonations and deprotonations, we ultimately get our alpha beta unsaturated ketone, our aldol condensation product. And as you can see, we don't have any steps numbered here. Everything is just thrown in together. So that is problem 3, an aldol condensation. Well, question 4 looks a lot like question 3 in that we're given the product and nothing else. So we have to fill in all these gaps over to the left of the slide. So this, what do we have? Let's classify our product. Our product includes a ketone, and by my eye, this is kind of a dangly group off of our ketone. So this is probably the group that got added. Note that it is added off of the alpha carbon relative to that ketone. So let's assume that this is how the molecule came apart. We started with a ketone and we added this piece. So let's just recreate our ketone in this starter material box. Right there. And now let's number our carbons. So we need to have 1, 2, 3, 4 with this cyclopentyl ring on there. So, I'm sorry, cyclopropyl ring. Now, let's see. We need to first make our enolate. So typically we use LDA. And I've skipped a step here. This is an enolate alkylation. So for an enolate alkylation, we kind of expect to see 2 steps. We need a base and then some kind of alkyl halide. So step 1, LDA, that's our base. That forms the enolate at the alpha carbon. And then step 2 is going to be addition of our alkyl halide. And I always like bromine, but you could put chlorine or iodine. That'd be fine. And this is going to be attached to carbon 1. And then our cyclopropyl ring. And that's it. That's our enolate alkylation. 2 steps. First treat a ketone with base, then treat it with an alkyl halide. Question number 5 again follows this pattern. We're given our product, but not the starter materials or reagents. So again, let's identify what kind of product we have. We have a ketone, and relative to the ketone, we have a beta hydroxy group. This is a beta hydroxy ketone, and these are formed from the aldol reaction. So we need a ketone over here, and in an aldol reaction we need to form an enolate. We're going to form the enolate at the alpha carbon, and then that enolate in the next step is going to attack a carbonyl, and that's going to have our beta carbon plus those 2 carbons. And then in the third step, we're going to have some kind of proton source. So this is going to be 3 steps if it follows the pattern. So let's go ahead and fill those in. What is our ketone? Well, our ketone is this piece right here up to and including that alpha carbon. The rest of this will be attached to our ketone. So there are some of the parts of the ketone come along at the beginning, and then of course we're going to add other parts of the product as the reaction goes. So we need to form our enolate. Good enolate forming base is LDA. And now we need to add this part. This comes from our aldehyde. So there's our aldehyde. That will become the beta carbon, and then we have 1, 2 carbons also being added to complete the product. And then the third step, we need to protonate what will be the tetrahedral intermediate once this enolate attacks the aldehyde. And so normally I just say add water. It could be an alcohol. Sometimes people will say HCl in water, so people will note that different ways. So that's our product. We've done an aldol reaction, and we have sort of our expected 3 steps here. So this sort of fit the template well. All right, question 6 actually gives us quite a bit of information. Not only do we get the product, but we also get the reagents. And note that we have 2 steps. 1, 2. The first is LDA, the base, and the second is an alkyl halide. So this is very likely an enolate alkylation with those 2 steps. So what is our product? Our product is this ketone, and we should get a ketone from an enolate alkylation, but presumably the ketone somewhere picked up an extra group off the alpha carbon, and that's not a very big group. That's just a methyl. But what do you know? Methyl is one of our methyl iodides, one of our reagents. So this presumably, let's number our carbons. Let's number with a pen. 1, 2, 3, 4. Those 4 carbons are presumably in the starter material. There's our alpha carbon, and then that additional methyl group comes from the methyl iodide. Now I think this problem is a little bit confusing because of the symmetry of this product. So you could, in theory, say, no, I think the starting material is this compound. And here's our alpha carbon, and we're going to deprotonate that carbon and put the methyl group over there. Well, as you can see, the compound or the starting material that we showed is the same as the starting material below it. They're just turned around. So from the same starting point, drawn a different way, but it's the same molecule, regardless what we do, if we do this methylation, we're going to get this same product. Note one last comment on this. When we deprotonate this starting material with LDA, there are actually 2 alpha carbons. So you might say, wow, where do we make the enolate? Well, LDA specifically deprotonates from the less hindered carbon. So we're going to make the enolate over off this alpha carbon, not this one. If you use a weaker base, we would deprotonate this one preferentially. But LDA goes after the more sterically accessible alpha proton. Okay, question number 7. All we're given is this product, and if we look at it, we can see it has a carbonyl that is alpha beta unsaturated. So this is an aldol condensation, which forms an alpha beta unsaturated ketone product. So we just need to tease our ketone out of here. So the ketone is going to include everything, including that alpha carbon. And then this piece over here with the beta carbon, that comes from our aldehyde. So here is our ketone. And there's our alpha carbon. Now, notice this ketone in this problem is the same as the ketone from the previous problem. So these are related, but notice that we have to form, to get this reaction to work, we need to form the enolate over here. Well, that's not a problem because typically aldol condensations use weaker bases, and the weaker bases tend to deprotonate at the more highly substituted side of a ketone. So again, we have 2 possible enolates we could form, 2 regioisomeric enolates, and we will tend to form this enolate if we use a weaker base. And we tend to use weaker bases normally for aldol condensations. So let's just put something in. Let's go sodium methoxide. You could use hydroxide. You could use ethoxide. I just chose methoxide to give a little bit of variety. Now, so that's our base. What is our aldehyde going to be? Let me fill this in. So there's a hydrogen also off that beta carbon. So the carbonyl this is what will become the beta carbon. It has 2 things on it. It has a hydrogen on one side. It has a phenyl on the other. That is an aldehyde, and that's typically the more commonly the electrophile that we see in an aldol condensation. So that is our aldol condensation. Note we just have one step, which is normally the case in an aldol condensation. We throw everything together, and eventually we get our alpha beta unsaturated ketone. Okay, this is problem number 8. Problem number 8 is going to be an exception to our rules, but we're going to go ahead and apply the rules that we saw in the methods that we saw in the first slide, and we're going to write out what we think our answer is. Then we'll critically look at that answer and see what needs to be fixed and how we can fix it. So we're going to start the way we always do. We're going to look at our product. Our product is an alpha beta unsaturated ketone. So this is going to arise from overall an aldol condensation. So let's identify our ketone starting material. Our ketone includes our alpha carbon plus the carbonyl, the ketone in the product. So that's easy enough. There's our ketone with its alpha carbon. And we know that our beta carbon is formerly a ketone in the reaction. So that's going to be a cyclohexanone. Now, let's number these carbons just to be clear. So if that's 1, 2, 3, 4, 5, 6. And there's our carbonyl that we attacked. 4, 5, 6. I hope that's clear enough. And then we just need a base in here. Typically when you do aldol condensations, you just throw in some kind of weak base. Let's see, let's use sodium ethoxide. And that's what we guess. Based on the guidelines in the first slide, and maybe a lot of the chemistry you've seen in your organic classes. Now, let's look at the problem. For the aldol condensation, everything is thrown together in the same flask. So, our base looks around for an alpha proton to remove. Now, yes, there is an alpha proton, but here is the issue. Our other carbonyl compound also has an alpha proton, and this happens. Sometimes you want to put together two carbonyl compounds, and both of them can form enolates. When that happens, you can't just use this typical way of doing an aldol condensation. We need to break up our steps. We need to form the enolate and then add the carbonyl. So, and when you say and then, you're implying that these are separate steps in time. So how can we fix this? Well, the way we can make sure that this ketone gets deprotonated to form an enolate is we can keep it separate and treat it with LDA. So this would be step 1. So that will give us this enolate. And why doesn't LDA deprotonate this ketone? Well, we haven't added that ketone to the flask. So this is the only ketone, so LDA will give us control over forming just that ketone. And we need to make sure you completely form an enolate, you need to use LDA. You can't throw in these weaker bases and just sort of let things do what they want. You've got to have control, so you have to use overly reactive, not overly reactive, but highly reactive reagents. Now, step 2, now that we have our enolate, now we can add our ketone. Now this enolate will say, aha, I see a carbonyl, and it can attack. Now this really looks like an aldol reaction. This is not the prettiest picture, but I think it'll do. So we have, here's our carbonyl carbon, here's our carbonyl carbon. This is now a beta carbon. And then, and that forms a tetrahedral intermediate. That is just going to float around until we add a solvent. I say solvent, it's not really a solvent. We need a proton source. We'll add water. And water will protonate that. I don't know why this is so hard. Okay, I just can't make my hand draw what my mind says. Okay, now we have a beta hydroxy ketone. Hydroxy ketone. So this is an aldol reaction to this point here in the lower right. And then typically, if you want to make the alpha beta unsaturated, then we could take yet a 4th step, and we could treat this actually with base or acid. I'm going to write base. And that will facilitate the loss of water to get our alpha beta unsaturated ketone. So this is a real exception. Okay, this answer at the bottom, this looks different. Step 1, LDA. Then step 2, add the ketone. Step 3, protonate things. And then step 4, treat it with a moderate base. That's very different from what we drew up here. This is an exception. The reason this is an exception is because we're trying to form an enolate from one carbonyl compound, and we need to avoid forming the enolate from the other carbonyl compound. So when you have the possibility of forming different enolates, you have to break the reaction up stepwise to make sure that you only form the enolate that you want. So that's an exception, but that's sort of an advanced one. But you do encounter these even in intro organic classes. You'll see this kind of reaction. I hope you found this video helpful for learning some general patterns in reactions of enolates. Please subscribe, give a like, or leave a question or comment. Thank you for watching, and remember that links to these problem sets are in the video description. Take care.